Hi, my name's Grady, and I'm going to be covering the presentation on how gravitational waves are detected and how they work. First, I'll be going through what gravitational waves are, and then some motivations, how the detectors work, and future applications. Gravitational waves are the wave-like distortion or the ripples in the structure of space-time caused by mass and energy that propagate through space at the speed of light. The idea was first introduced in Einstein's theory of general relativity as the consequence of accelerating massive objects. Now, why is it important to study these phenomena? As you can guess, they're very hard to detect and require a very large excitation of space-time to be noticeable. This might make you think, how can I even use this? This isn't entirely useful in our day-to-day lives, however, it does seem to be very useful in astrophysics. With gravitational waves, we can detect cataclysmic events in space, such as black holes colliding or even the very beginning of the universe. It also allows us to obtain a new view of the universe altogether, completely different from the traditional methods of astrophysics. Before we go deeper into these applications, we need to understand the problem with light. Light can be easily obstructed when propagating in space. This is a huge issue since almost all of astrophysics depends on light. If we try to observe astronomical events like a black hole collision using classical methods, we may see the brief light produced in the collision, but the point of a black hole is that light doesn't escape them, so we lose a lot of the information. That's where gravitational waves come in. They're independent of electromagnetic waves, making it easier to see these events. Also, gravitational waves are almost impossible to interfere with, making it a great alternative to light. Now let's look deeper into how it works. For the first time, the detection of gravitational waves was successfully observed by the Laser Interferometer Gravitational Wave Observatory, or LIGO, on September 14, 2015. LIGO is the world's largest gravitational wave observatory, comprising two laser interferometers located 3,000 kilometers apart. The interferometers are L-shaped, with each arm being 4 kilometers long, and includes a light source, 2 mirrors, a beam splitter, and a photodetector, all contained inside a vacuum chamber. This parallels the MZI, which we are familiar with, superimposing the beams of light and observing their interference pattern from the alignment of the waves. The procedure is as follows. A laser beam is emitted and is split as it travels through the beam splitter, shooting down each arm, then reflected by the mirror. As we expect, if the distances are the same, the realignment of the waves yields destructive interference and no light is observed. Thus, if the distance even slightly varies, the waves are no longer perfectly aligned and a flicker of light is observable. But what if this distortion is 10,000 times smaller than a proton? Now, let me cover the calculations behind the detection process. Gravitational waves generate a differential arm oscillation. This oscillation is space-time stretching along one direction and compressing in the perpendicular direction. So, as a gravitational wave is passing, LIGO's arm changes by the tiny disturbance in opposing ways. This distortion in space is equivalent to a phase shift of phi, similar to the MZI. Therefore, the output state of the photon in LIGO with the presence of a gravitational wave can be described as a matrix with the phase shifter factor e to the I phi. To determine phi, we first calculate the probability of detector 1 and 2 using the Born rule, which we can see here. We can also see that the calculation is exactly the same as homework 1 question 3. Again, this is because the distortion of space is caused by the passing of a gravitational wave acting like a phase shifter, and because the laser is reflected back through beam splitter 1 twice, we can assume that it is equivalent to 2 beam splitters. We can then solve for phi by subtracting the two probabilities and rearranging the equation. This gives us the inverse cos of P2 minus P1. Furthermore, for n number of experiments, the counts in detector 1 and 2 are defined as n1 and n2 respectively. We can then estimate the probabilities of P1 and P2, yielding us a more practical form to calculate the phase shift, which is phi equals the inverse cos of n2 minus n1 over n. Now we know how to calculate the phase shift. However, there are countless sources of vibrations on Earth, and billions of times larger at that. How can we determine whether or not such impossibly small perturbations are actually belonging to a gravitational wave? To filter out terrestrial vibrations, two identical detectors are situated in isolation 3,000 kilometers apart. This separation takes into consideration local vibrations, gravitational wave travel time, and source localization. Naturally, if LIGO's detectors are to identify incredibly small cosmic distortions, they are extremely sensitive to tiny vibrations. Many factors cause disturbances that can mask or mimic gravitational wave signals in each detector. By separating them at large distances, it ensures each one experiences local vibrations unique to the other. When the data is compiled, computers compare and emit different vibrations and keep signals that look the same. The elapsed time of a gravitational wave traveling between both locations must also be considered. Since they travel at the speed of light, only similar signals that occur within 10 milliseconds of each other would be the result of a passing gravitational wave. Any other similar signals that are longer than 10 milliseconds apart are filtered out. Finally, two detectors allow us to pinpoint the direction of the gravitational wave signal. The more gravitational wave detectors around the world, the narrower any source can be localized. There are many ways we might be able to detect gravitational waves in the future, such as using millisecond pulsar arrays to detect weak gravitational waves. Space navigation using pulsars was first theorized by G.S. Downes in 1974 with a 1,500 km error, later reduced to 150 km by Chester and Buttman in 1981 using X-ray pulsars. Modern applications focus on millisecond pulsars with a margin of error within 30 km. Millisecond pulsars are highly magnetized neutron stars spinning within a few milliseconds, which are formed by a stellar collision that transfers rotational energy into old and stable pulsars, which creates incredibly precise natural timers. With automated navigation and pulsar timing, interplanetary and interstellar navigation become feasible. Due to the precision involved with this method, small variations are very noticeable. Timing is affected by factors like Shapiro delay, Einstein delay, and pulsar glitches, but the timing residual is where we find our wave. The correction term omega in this residual is the direction of the gravitational wave, and the delta H is the difference in magnitude between the pulsar and Earth. These variations allow pulsar timing arrays to function as low-frequency gravitational wave detectors in the range of 10 to the negative 7 to 10 to the negative 9 Hz, measuring space-time distortions by calculating this residual. This is becoming increasingly possible due to advances in AI, which will allow for quicker comparisons of the large data pools. We are likely to see the first use of this method within the next few years thanks to timing arrays like China's FAST and South Africa's Meerkat. Thank you. That was my discussion on how gravitational wave detectors work, and before I leave, I just have a quick question. How is the math involved with calculating a gravitational wave similar to that of an MZI with a phase shifter?